power functions kind of are the functions that make up polynomials, right? So they're a little bit more general than that, but examples are x squared or x cubed or x to the 1/2 or 1 over x, which is really x to the -1. Okay? So here's some examples of power functions. We call these power functions. Okay? The idea is that it is x raised to some power. Right? And it is worth noting that these are the building blocks of polynomials. X squared, x cubed, x to the 4th, x to the 5th. Right? There are other functions too, things like x to the 1/2, which is the square root of x, or 1 over x, which is x to the -1, that are also power functions. But if I knew about all power functions and how to take the derivative of power functions, then that might start to give me some insight into polynomials also. So I'm going to primarily consider right here these integer powers, 1, 2, 3, 4, and see if I can't come up with some general type of rule about those power functions so that I know something about polynomials, and hopefully I can extrapolate rules for those functions to kind of go to all of the other ones, right? So this is kind of a general theme that we might find. Let me tackle the easy cases, and hopefully I'll come up with some idea about how the more complicated cases would work also. Some of these we already know, right? So the derivative of x is what? It is 1x plus 0. So its derivative is 1. That's the slope. That is the coefficient in front of the x. And previously we have seen this one. We've seen x squared. We did that one as an example previously. Its derivative is 2x. And if I wanted to, I could try to kind of continue down the line to see whether I saw a pattern, right? So if I took the time to evaluate the derivative of x cubed, I think there was one problem in the homework set that had an x cubed in it, which was probably horrible for everybody. Hopefully after today it will be less horrible. I would find that the derivative of x cubed is 3x squared. Right? There's a lot of work that goes between here on the left side to here on the right side, right? The limit as h approaches 0 of x plus h cubed minus x cubed all divided by h. And then you got to expand, right? And then simplify, and eventually try to factor out an h and cancel. But at the end of the day, you would get 3x squared. So x cubed is going to 3x squared. And if I hated myself even more, or I was watching something with a lot of commercials or something like that, I might sit around and do the algebra long enough to find that the derivative of x to the 4th is 4x cubed. So if I did all of that work, what do you suppose the derivative of x to the 5th is going to be? Do we see a pattern that this is following? 5x to the 4th seems likely. Okay. What about the derivative of x to the 20th? 20x to the 19th. Seems like it could be. Right? I don't really want to do the algebra to test that out. I will tell you that it is true. Right? The idea in general here is that x to the n, right? The exponent goes out front, right? This x squared, the 2 became a coefficient. X cubed, the 3 became a coefficient. X to the 4th, the 4 is telling me the coefficient up front. X to the 5, there's a 5 out front. X to the 20, there's a 20 out front. So x to the n there's an n out front. Whatever that number is the number that's out front. And then x, and then what's the power of the x? Yeah, it's 1 less, so n minus 1. So here it is in a box. Here's how I take the derivative. Let me put a ddx on that arrow so that I know that we're taking the derivative. Right? X to the n, you take its derivative, you get n x to the n minus 1. And it seems to follow this pattern for integer powers, or at least positive integer powers. What does that mean for other things, right? What about 1 over x? What would the derivative of it be if we followed that rule? 1 over x, remember, is x to the negative first power. So negative 1 times x to the negative second power, right? So the exponent becomes a coefficient, and then I reduce the power by 1. So negative 1 minus 1 is negative 2. So that's negative 1 over x squared. That seems like it might make some sense, because at the beginning of class today, we saw that 3 over x got turned into negative 3 over x squared. So we saw something that looked very similar to this at the beginning of class today, and we did it the hard way. But if we use this power rule, it might happen a lot faster. What about another one that we saw at the beginning of class today? The square root of x. This is x to the 1/2 power. G prime of x is what?
1/2 x to negative 1.
Yeah. Okay. So the exponent becomes a coefficient, and then I reduce the power by 1. So 1/2 minus 1 is negative 1/2. If you had 50 cents and then you owed me $1, you would have negative 50 cents. Negative 1/2. And that is 1 over 2x to the positive 1/2. Right? I don't like negative exponents, so I can move it to the denominator in order to make the exponent positive. And remember that a 1/2 exponent is a square root. So if I wanted to write it a different way, I could write it as 1 over 2 square root x. And we did that exactly earlier. And that's exactly what we got. So I'm feeling pretty good about this rule. Right? And it turns out that it is true in general. Right? So it works for polynomials. It works for 1 over x, 1 over x squared. It works for roots. It works for a square root or a cube root or a fourth root. It would work for something like k of x equals x to the 3/2. Right? X raised to a number. What is k prime of x going to be? Right? The exponent becomes a coefficient, x, and the new power is 1 less than the old power. Right? So 3/2 minus 1, 1 is really 2/2. So that's leaves 1/2. Easy enough to do. Okay. So, awesome. Well, so I'm starting to get to a place where I might be able to do polynomials. Okay? The previous example allowed me to add things together. So what if I had something like h of x equals x squared plus x plus 4? Here's a polynomial. What's h prime of x going to be? I'm adding functions together, and we saw previously, beyond any doubt, we found that if you're just adding functions together and you want to take a derivative, you can just take the derivative of each term. So the derivative of x squared is
Two x.
2x to the first, so 2x. And the derivative of x is 1. And the derivative of 4 is 0. Okay? So that's 2x plus 1. There it is. Easy. Why didn't I show you this last week? So you didn't spend all weekend doing it the hard way, right? What about this, though? Not all polynomials look like this. Sometimes we see things like m of x equals 3x squared minus 5x plus 10, something like that. Yeah.
So none of this is going to be on our exam. Like, are we not allowed to use this on our exam?
You will not be allowed to use this only, right? So feel free to use this to kind of verify your answers. But if I were to ask you to use the definition of the derivative in order to find,
definition 1 or 2.
yeah, I will ask you.
5 and 6.
I will just say use the definition of the derivative to find the derivative of blah blah blah.
Okay.
And if I do that, don't do this.
That sucks. But if you say nothing, can we use it?
I won't say nothing.
Okay.
The exam will focus on limit stuff, and it'll focus a little bit on the idea of the derivative. So there might be concept types of questions. I would include like, what does the graph of f look like as a type of concept question. Right? Is the derivative positive here or negative here or 0 here? There will only be like one problem where I ask you to find the derivative by the definition. And that will be the last time in this class that you will ever see a problem like that. Because this is so much better, right?
Yeah, that's good.
But it's important. I mean, I think it's important to kind of know how that concept ties into the definition. That's really what's happening here, right? When I find h prime, this represents a limit of h of x plus h minus h of x all divided by h. Right? This represents me evaluating that limit. It's just there's a nicer way for me to do it than having to go through that whole process. So the problem I have with m here at the bottom is that suddenly there are all of these numbers. There's the 10 I'm okay with. I know what the derivative of 10 is. It's 10, so 0. Right? It's not changing. But now I've got 5x. That's okay too, because this is linear, so the slope of negative 5x is negative 5. But now there's this 3 in front of my x squared, and I'm not super happy about that, right? Because my rule, if we remember, right? My rule says if you have x to a power, you get n x to a different power. Okay? So what happens if there's a number in front of this? Does everything get screwed up? We will multiply. So let's see how that works. The rule is this. The rule is that if you have c f of x and you take the derivative, you get c f prime of x. So if there's a constant multiple in front of your function, it's just going to stick around. It's not a big worry. Right? That is to say, the rate at which the function is changing, if you multiply it by a factor, just multiplies by that same factor. Right? If all of your f of x's are twice as big, then the rate that it's changing is twice as big. Right? If it was changing from 1 to 5, and now it's changing from 2 to 10, how much change there was also doubled. So that's all this is saying. That's what this is saying in the context of what a derivative is. Yes?
Would you do 3 times 2? Which
Yeah.
would be 6x.
So 3x squared would get turned into 3 times 2x. Right? Because 3 is a constant multiple. So it's just going to stick around. And I just have to differentiate x squared, which is 2x. So 3 times 2 is 6. So 6x. That's the idea.
And then could you find another derivative? Could you do like a derivative again?
Yes, I could. And we'll talk about that after a short break.
Okay.
So before we go, though, let's look at another example. let's look at something like 6x cubed minus 4x squared plus 9. Okay. So f of x is 6x to the third power minus 4x to the second power plus 9. So what is f prime of x?
18x squared minus 8x.
Absolutely. Right? The 6 doesn't really matter. Right? The 3 will come down, so I have 6 times 3 is 18. I reduce the power by 1, so 2. So 18x squared. Right? The 2 comes down as a coefficient. 4 times 2 is 8, so minus 8. And then x raised to 1 less. 2 minus 1 is 1. And the derivative of 9 is 0. Anything plus 0 is 0. It's just itself, right? So there we go. 18x squared minus 8x. A lot easier to do. So now we can do any polynomial. We can also do things like what we saw at the beginning of class, right? 3 over p. Remember, that's 3p to the negative 1. So f prime of p is negative 3 p to the negative 2. Okay. The exponent becomes a coefficient, so 3 times negative 1 is negative 3. And we reduce the power by 1. Negative 1 minus 1 is negative 2. And here we are, negative 3 over p squared. Great. Super easy to do.